So, the graph of v of t is shown to the left. It shows the velocity of a car in feet per second traveling along a straight highway. We are supposed to find the integral from 0 to 7, and that shouldn't say until describe its meaning, and describe its meaning. So, if we are looking at the velocity here, and we want to find the integral from 0 to 7 of v of t, then we are, 7 is right here, we're finding this area right here underneath our curve. So that's a trapezoid. If you want, you can break it into triangles and rectangles. That's fine. I'm going to do a trapezoid here. For a trapezoid, your area of the trapezoid is going to be 1/2 times the height. The height of this is 2. And then base 1, which would be 7. And then the top base is 2. So that is going to give us an area of 9. So the integral from 0 to 7 of v of t dt equals 9. Okay, and it will be 9 feet. I know that it's going to be feet because for my velocity, it's measured in feet per second. So the x-axis here is my time. It would be seconds. This would be feet per second. So if I am finding the integral, the area, I multiply those together. Feet per second times seconds, and the seconds cancel, and I just have feet. So we've got to describe this in words, what it means as far as this car here. So anybody want to take a try? Take a stab at this one. Okay, Thomas, tell me what you were going to say there.
Over the course of 7 seconds, the car is traveled 9.
And I might would say the first 7 seconds. Just because if you mean any 7 seconds, it would not necessarily be true. But we're talking about 0 to 7. So over the course of the first 7 seconds, the car travels 9 feet. A lot of times we'll make up these problems. I don't see if they make sense. 7 seconds is a long time for a car to go 9 feet. Maybe somebody's pushing it. Because you should be able to drive a little faster than that. That first part's really important. Over the course of the first 7 seconds, you need to make sure it is a range of time. So you could say from 0 to 7 seconds. You could say, I like this over the course of the first 7 seconds or during the first 7 seconds. But it needs to be that time range. Do not say at 7 seconds. Because it's from 0 to 7 that you have to be talking about. Yes, that's what it means when it says describe its meaning. And you will see this a lot on the FRQs. Yeah, you can. As long as your lines are straight, it will probably work. But if you have a curve, then you're going to really have to do a little more calculating. Because a guess will not be good enough. Like you could probably you would have to guess exactly 9. So like if you guessed at 8.5, you would not get any credit for that. They didn't ask for an approximation. So if you did the squiggly line, they would not take it. Unless they asked for an approximation. And if they did that, it's usually a tangent line approximation. Yes? So the height of that trapezoid is this right here. So that's the 2 right here. And then your base 1 is 7. So that's this. And your base 2 would be this side right here. So that's where the other 2 comes from. So trapezoid, that's a formula they're not going to give you on the AP exam, and I'm not going to give you on any problems that you have. So for trapezoid, remember it's 1/2 times the height times base 1 plus base 2. So make sure that's one that you have memorized. I guess you can get around it a lot of times by doing triangles and rectangles, breaking it up there. But trapezoid's a little quicker. I don't know why I have 18 here. I think that's supposed to be a 10. So let's change that to a 10. Pretty sure it was supposed to be a 10. And I wonder if I really meant 9 to 10. I guess we'll go with it. I might have meant to do 7 to 10. I'm not sure what exactly I was doing. So, same graph and same situation as number 1. If I'm finding the integral from 9 to 10 of v of t dt, then 9 to 10 is just this area right here, which you definitely can just count here is 4. But because it's below the x-axis, it would be negative. So, in this case, it would mean that the car is going backwards 4. So maybe somebody was trying to push it up a hill, and then they fell down, and then it started rolling backwards again. Hopefully not over top of them. Hopefully just rolling back, maybe. So we would say from 9 to 10 seconds, the car went backwards for feet. I think they would prefer you to say backwards. If it traveled negative 4 feet, I think that's one of those things I think they'd probably give it to you. But I'm not certain.
What if you just use like this funky wording and say like from 9 to 10 seconds the car went forward negative 4 feet, and then you just did that consistently through the whole exam?
I would not want to risk it doing that. What I know you definitely cannot do is you cannot say it went backwards negative 4. If you said backwards negative 4, that would be wrong. You would not get credit for that. If you say it traveled negative 4 feet, you might could get away with that.
That's not how
I think I'd let it slide, but I'm not certain. Okay, so the last thing asked is for the integral from 0 to 10 here. So we already found this area right here, it was 7. This part right here was it was at 8. Oh, well, that did erase.
I'd say 0.
I thought it was a 0.
The top number is an 18.
It was an 18. I'm making it a 10.
What are y'all talking about, man? That's
Example 3.
No, but 3 is infinite.
9 times 2. Yeah, it's 9.
Okay, you're just. Are you giving me the answer?
Yeah.
I don't think the answer is 9. All right, so this area right here was 4, and then you got. This is also 4. So the integral from 0 to 10 of v of t dt from, it would be the integral from 0 to 7, which is 7. Was it not? What was it? Oh, I get what you're saying now. Okay, sorry. Thank you. I was confused on what you were saying was 9. Okay, it was 9. And then we would subtract the 8 here. So we would just get 1, and this is again feet. 1 foot. Alright, so what does this mean?
It means overall cars only travel a singular foot.
Okay.
That movement of 1 foot.
Okay. Okay, I like the way Selena said it. Because if you say over the 10 seconds it has only traveled 1 foot, that sounds like you're telling me the total distance it traveled. How far, what's its total distance? We're integrating velocity, which is going to give us position. Correct. So we could say at 10 seconds, the car is 1 foot away from its position at t equals 0 seconds, or you could say its starting position. That would be good. I also heard the word displacement. That's another good thing to say. That is why it might be better to say that over the time period it went 9 feet in the positive direction and 8 feet in the negative direction. So if you say it moved 1 foot, it really went 17 feet total. So the best thing a good thing to do here over the time period from 0 to 10 seconds, the displacement of the car is 1 foot. So using that word displacement there, you could maybe say in the positive direction here if you want, but I think just using a positive 1, it would be fine. Say that again, Chandler. Why? Oh, it's okay. So you got to remember, this is velocity. The graph we're looking at is velocity, not position.
That's why.
Yeah. So this is like looking at the derivative graph.
So why is
If they had given you the position graph, that is exactly what you would do, and the displacement would be 4. Yeah. But this is the velocity graph. Correct.
Why is it whenever you take integral of the velocity of position?
So integrals are the inverse of derivatives. So normally, everything we've done, we've started with position. So we had like our x of t, that was position. And then we took the derivative of that, and it gave us velocity, right? X prime of t is velocity. So that was taking the derivative. If we want to go backwards from velocity to the position, we would integrate. There, it's kind of like like adding and subtracting. They undo each other. So if we integrate, it is going to give us position. Yeah. And similarly, if like we had acceleration and integrated that, it would give us velocity. Yeah. Correct. Okay. Yes.
I don't know what it is. I don't want to.
It is. Okay. Okay. So if the car is located at the point x equals 0 at t equals 0, so let's say it started at 0, then find the values for the position x of t at each point listed on the table. So our position at 0 is 0. We were kind of assuming that in the way we were speaking earlier, but now it's telling us that for sure. So at 1, I've got 1/2. It's going to be a third.
What? No, that's a half. That is a half.
It's a fourth. It's half of a half.
Oh, really?
No. The area of that tiny triangle. Yeah. Because this graph is still our velocity graph. So to find x of t, to find position, we're doing area under the curve. So that would be, the height of that would be 1/2. So half times 1 times half would give us 1/4. At 2, we'll have 1 because the area of that triangle there is 1. Right. I'm talking about all the way from 0 to 2.
Okay.
Right. The base right there is 2. The height is 1. So if you do 1/2 times 2 times 1, you would get 1. All right. So right here, that looks like 1.5 times 3. So 1/2 times 3 times, let's do 3/2. There is going to give us 9/4 or 2.25. The area of this triangle right here. Right, so you're doing 3, and then the height right here is 3/2. Then, if we move on to 4,
So I said 2 1/4.
2 and 1/4 same as 9/4.
I didn't follow what you were doing.
Yeah.
No, I got it right.
All right. And so here we'll have 4. Area that's 1/2 times 4 times 2. Here at 5 we start getting ones where we can just count the blocks. We've got 6. At 6 we'll have 8. At 7 we'll have 9. Okay. Right here at 8, what are we going to have? Not 10. We're going to have 8. Because this area has an area of 1, but it's negative. And at 9, I don't think 7. This has an area of 1, 2, 3. So we'll subtract 3 here, we'll get 5. the area here. So from 8 where we were at, we've got 1, 2, and then 3 if we count those together. So we subtract 3. And I don't know why I didn't do 10 for whatever reason, but let's just go ahead and do 10. At 10, our position would be, we subtract 4 more, and we get 1. That's what we got earlier. Right. Actually, I probably do know why I didn't do 10. I think that it only lets me add so many rows to my... Yeah. Okay. Ethan, do you need a new mask? Okay. Okay.
It is protecting the school with every fiber of its being.
Okay. So, we've only got 12 minutes left. I think we'll be okay. It's not worth waiting.
National security.
Yeah. Okay. So, all right. So, if we notice what is happening here, we can look at our position that we have. So when we integrated, for example, from 0 to 7 of v of t dt, we got an answer of 9, right? So that could have been just the 9 that we got here, but you would have to subtract your starting value, in this case was 0, right? So, that's a 9. If I wanted to integrate, if I want to know how far it traveled from, let's say, 2 to 4, okay? So the integral from 2 to 4 of v of t dt. Now this one, I could look at that area on my graph. I could go from 2 to 4 and find that that area there was 3. Or if I'm looking at my position, I could take the position at 4, which was 4, and subtract the position at 2, which was 1. That would also give me 3. All right. So I'm just making up a problem here. Let's say that I wanted to know the integral from 2 to 4 of v of t. Right? So I could look over here at my graph, and right here's 2, right here's 4. I could just find the area of this area right here, which is 3. Another way that I could do that same thing is I could just take my position at 4 and subtract my position at 1. It would show me how far that particle had traveled. All right. So what I did there was I found x of 4 minus x of 2. So this is position at x equals 4 minus the position at x equals 2. And this would be true for anything here. So if I'm going from 0 to 7, I could also do x of 7 minus x of 0. Right? X of 7 would be 9. X of 0 would be 0. That would give me 9, which was that area underneath that curve. To find our change in position, we could integrate by finding that area under the curve, or sometimes we don't have that information. We don't have the graph, or if we do have the graph, it's a curved line where we can't figure out exactly the area. So the other thing that we can do is we can say that the integral is the change in position. So we can take position at this time minus the position at the other time, which we're eventually going to get to where we can find without having the graph. So this is another iteration of the fundamental theorem of calculus. It basically tells us how to evaluate. It tells us how to evaluate a definite interval. So here, whenever we're talking about this, capital F prime of x equals f of x. So f would be like the original function. F prime would be the derivative. So if we are integrating f, most of the time if we integrate a lowercase letter, we say that its integral is capital F. So the integral, the area under the curve of f of x from a to b would be capital F of b minus capital F of a. Yes. Yes, it would be like, so if little f was like velocity, big F would be like position. And we're going to learn by tomorrow how to do that with all equations, or not all equations. Correct. So we're not like solving for an answer right here. So if I'm integrating from 1 to 4 v of t dt, the integral of v of t is going to be x of t. And I'm going to write this step right here because this is some notation that we're going to use later. So when I integrate v of t, I just get x of t. So the integral of velocity is position. And then I'm putting this bracket here that tells me I'm evaluating that from 1 to 4. And so that is going to equal x of 4 minus x of 1. And our x of 4, that is position at x equals 4. And this would be position, actually I should say t equals 4 at t equals 1. Basically our displacement that we have, right? Our position of where we ended up minus the position of where we started on this interval that we're looking at. It should be a t. Yeah, both of those should be t's. No. There's not really homework on this section. Homework's going to be a little bit different. So if I have the integral from 0 to 3 of a of t, what is the integral of acceleration? Velocity. So integrating acceleration is going to give us velocity. To evaluate that, you would always put that top number first. I'm sorry, I don't know why I did 1 and 4. Looking at the last problem. This is 0 and 3. There. And so to evaluate that, it would be v of 3 minus v of 0. So this would be different. This would be our change in velocity, right? So this would be velocity at t equals 3, and this would be our velocity at t equals 0. So we still have some that we need to look at here quite a bit, actually. But good news is you can still do your homework.